Hello everyone! Disney movies are filled with tons of distinctly different surfaces, from sparkly snow to skin to linen. All these materials behave differently enough that you'd think each one is programmed individually. But actually, everything in the scene uses the exact same mathematical model, enabling artists to model as many materials as they want, with just one very powerful tool. The math that drives Disney's shading model is the same math that drives every modern shading model. From ultra-photorealistic graphics to Disney's and DreamWorks' stylized graphics, this is what connects it all behind the scenes. It starts at the beginning with the god of graphics, our guiding star, the one that points the way. The rendering equation. While it might look complicated, by the end of this video, you'll understand how games with ultra-realistic graphics like God of War are only a few lever pulls away from looking like Wreck-It Ralph. Most people are never taught or come to conceptualize what math actually is. Math is not real. It is essentially a cartoon of reality. By taking measurements and making personal observations of real-world phenomena, we do our best to construct mathematical models that closely match the behavior that was measured or observed. With a proper model, we can use it as a replacement for reality to predict future outcomes, or in the case of computer graphics, visualize the results, or make intentional adjustments to the model to stylize and create a new reality. Once you get to any problems of substance though, you begin to understand just how diverse, unpredictable, and chaotic the real world is, and math switches gears from talking in simple absolutes to talking in hypotheticals to obtain good enough approximations. Rather than knowing the solution, we model what a solution should look like, and if a solution exists, it matches what we need, essentially a model for a model. This brings us to this video's problem. Given a point on a surface, how do you determine how much light is going out in a specific direction? This is the fundamental problem of computer graphics, as the resulting light ray from this process becomes the color of a pixel in the final image render, so it's like the most important part. You might be thinking, if the problem can be described in one sentence, it must not be that complicated. But if you take a moment to look around, you can immediately prove yourself wrong. Just looking to the right from my computer, I can already see at least 10 surfaces that all behave in very different ways. Even the plastics are distinct from each other. While we can totally model each surface individually, there is one thing that connects them all: the fact that light goes in and light goes out. So if we want a general model that can do it all, then we need to start at the highest level of abstraction and construct a more sophisticated solution on top of it. This brings us to 1986, when David Immel and James Kaguya introduced a general equation to describe the expected behavior of light surface interactions. Bear with me here, this one is a lot to take in. The amount of outgoing light at a point on a surface is equal to the emitted light plus the reflected light. This is the rendering equation. If you think this is too simple, just remember that you're the one that convinced yourself that math has to be complicated. The rendering equation is the holy mother of graphics, and every lighting model across every engine is an attempt to solve it, whether intentional or not. I say attempt because there is no exact solution. Everybody has their own solutions, with their own pros and cons, as well as subtle differences. This is why you can usually tell if a game is made in Unreal, because you're familiar with the Unreal Engine lighting model at this point, whereas a game made in a proprietary engine has its own approach, and thus feels a little bit different enough to be unique. Today, we'll be looking at Disney's solution to the rendering equation, and how they used just one shading model to create every single distinct surface in Wreck-It Ralph and future movies, which is quite the powerful tool. But first, something a little different. This video has been sponsored by Helix. Helix provides premium mattresses customized to fit your needs, conveniently shipped to your door. Helix's sleep quiz matches you to your ideal mattress. Just answer a few questions based on your sleep preferences and body type, and Helix will recommend you the mattress that you've been looking for. I was matched with the Helix Dusk Luxe, and after sleeping on it for a few weeks, I couldn't be happier. I'm haunted by terrible nightmares and regularly wake up in pools of sweat with a vulnerability stack before I either go back to sleep or decide I've had enough. Thankfully, Helix offers an option for the Glaciotex cooling cover, which enables the mattress to better diffuse heat and keep you cool, especially during the summer months. Since sleeping on the Helix mattress, I haven't woken up sweaty once, even though it's already really hot outside. Jokes aside, I'm actually really happy and impressed that the mattress was able to solve my temperature regulation problems, and I don't wake up as much anymore. Additionally, Helix mattresses are fiberglass free, unlike many other mattress companies that make make use of fiberglass as a flame retardant, which studies have shown can lead to numerous health issues, since breathing fiberglass is bad apparently. Helix is committed to keeping fiberglass out of your lungs by manufacturing their mattresses in their own facility, so you can sleep easy. Helix makes getting a new mattress easy by shipping straight to your door. The mattress comes rolled up in a box and takes no time at all to set up. Along with free shipping inside the US and a 10-year warranty, Helix also offers a 100-night sleep trial to make sure the mattress is right for you, so trying something new is totally risk-free. If you're looking for a new bed, be sure to check out Helix's wide selection of 20 unique mattresses and take advantage of their Memorial Day sale with 30% off Luxe and Elite mattresses or 25% off site-wide by following the link on screen or in the description. Thanks so much to Helix for sponsoring this video. Okay, you're right. Maybe the equation is a little too simple, but it communicates the fundamental idea. The part we mostly care about is the reflected light portion, because emissive light is usually just an additive constant when we want to model something like a light bulb or anything else that produces light. If we wanted to make that fancier, like have an emitter that is anisotropic or strobes, then we would make modifications to that portion of the equation, but otherwise, we can kind of just ignore it, since most surfaces are not emissive anyways. Without emission, the equation reduces to just the outgoing light being equal to the reflected incoming light, and now we have to convert this abstract idea into math that achieves the described behavior because a computer doesn't know what these words mean. Using the least amount of math possible, we define a few variables, such as the position in space, the direction of outgoing light, which is the direction towards the camera in this context, the direction of incoming light, and the color of that incoming light. Then, to solve the rendering equation, we set the outgoing light equal to the incoming light, and we're all done. To set the scene for our amazing new model, imagine a sphere in a black void with absolutely no light except a single directional light source colored white. Well, that's obviously not right. We are getting what we asked for though. Each point of the sphere is outputting the color of the light source without regard to anything else. If we look at the real world though, we can see that a directly lit sphere looks a bit different. It's brightest where the surface can see the light and slowly gets darker until the surface faces away from the light. Clearly there is a relationship between the direction the surface faces and the amount of light reflected at that point. This means we need a new variable, which is the vector that points orthogonal to the surface, the normal vector. For a flat plane, this vector points directly up. Visualizing the light vector here, if it's directly overhead the normal, then we should expect a full strength reflection, but as the light vector moves away from the normal, below a 90-degree angle, clearly the light should no longer be able to reach that point, and there should be no reflection as the surface itself is blocking the view. Coincidentally, a function exists that takes in an angle and returns 1 when the angle is 0, and returns 0 when the angle is 90 degrees. This function is called cosine. So what we need is the angle between the normal and the light direction, which we call the incident angle, to put into cosine. Thankfully, we can skip that entirely by making use of a linear algebra operation, the dot product. There are two ways to calculate the dot product. The first is by multiplying each component of the vectors and adding them up, or by multiplying the magnitudes of the vectors by the cosine of the angle between them. Since our light and normal vectors are normalized, their magnitudes are equal to 1, and any number multiplied by 1 is the same number, which means the dot product will be equal to just the cosine of the angle. So, if we use this first formula, then through the equivalence of the two definitions, we get what we need. Back to our model, we can write this as either the dot product of the two vectors, or as the cosine of the incident angle. It depends on who's writing the equation. Wikipedia uses the dot product, but Disney uses the cosine, so I'll do that for consistency across resources. The cosine is multiplied with the incoming light color, which attenuates it as the normals of the sphere begin to point away from the light source. But there's one problem. Our lighting is backwards. This is because our incoming light direction is the actual direction of the light, and if we compare the two vectors, we're getting the wrong angle. So in order to simplify, we want our incoming light direction vector to point towards the light source. That way, our dot product trick actually works. If we wanted to model what a white sphere with perfect Lambertian reflectance looks like in a black void with a singular directional light source, We'd be really on the money here. We want a model that can output many kinds of surfaces though, if not every kind of surface. Currently, our model assumes an equal scattering of light in all directions, which we can visualize as a 1. This is obviously quite limiting and fails to accurately portray any surface that is not a perfect light diffuser. As we can see, most surfaces do not scatter light equally in all directions. Shiny surfaces have pinpoint highlights. Mirrors do not diffuse any light at all, and some metals even change the color of their highlights. There's such a wide range of complex behaviors here that we have no choice but to once again take an abstract approach and use a placeholder function that describes how much light is reflected at a specific point. This function is known as the bidirectional reflectance distribution function, or BRDF for short, and is the real meat of the rendering equation. We still have some things to add though. For instance, we're only taking into account one light direction, but if we wanted to get the true amount of incoming light at a point, we would need to check every single possible incoming direction in the surrounding hemisphere, which is how we would get global illumination and soft shadows, as observed here, where the light has bounced off the floor and onto the sphere. In math, we model this using an indefinite integral, because there are technically an infinite amount of incoming directions. In real-time rendering though, we're just going to compute 1 or 2 light directions and ignore the integral. Lastly, we bring back our emissive light term from earlier, and we have derived the actual rendering equation written in math terms, not just abstract ideas. This version is a bit outdated though, as it doesn't account for a number of other aspects of light behavior, such as transmission of light observed in translucent surfaces like glass or water, subsurface scattering of light observed in surfaces like jade or foliage, polarization of light, which is hard to explain, phosphorescence, which is when a surface slowly releases light it absorbed earlier, like glow-in-the-dark stars, light interference, which is when the wave of light is interfered with just like other waves can be interfered with, fluorescence, which is like phosphorescence, but the glow ceases immediately after radiation exposure stops, nonlinear light effects such as two-photon absorption. If you want to read about atomic physics, you can go ahead and do that on your own time. Lastly, the Doppler effect also applies to light, but only when objects are traveling close to the speed of light, so we can probably just ignore this one. As you can see, light is pretty complicated, so we usually generalize all of this behavior underneath the umbrella term bidirectional scattering distribution function, or BSDF for short, which our BRDF falls underneath. While theory can capture all of this, it's easier said than done because we're limited by our computers. As graphics programmers, we have to compromise on realism based on what we can efficiently compute, and the most important part of it all is the BRDF. So most resources are going to be focused on that, including this video. If you've seen my previous videos, I've already taught you a few BRDFs just without calling them that. So let's do a quick review of those and determine if they are actually solutions to the rendering equation. While it may not be initially obvious to people less familiar with math, this simple equation enforces a set of rules on our solution in order for it to be valid. For instance, the equality operator is doing a lot of heavy lifting. It ensures that our solution does not break the law of conservation of energy. The outgoing light can't be greater than emitted and incoming light. Essentially, we can't produce more energy than was given, as that would break the laws of physics. Another restriction is in the BRDF. It's called bidirectional because the output should be the same if the incoming and outgoing directions are swapped. This is known as the Helmholtz reciprocity principle, which I explained in my last video. These two rules are what we'll check against when verifying our rendering equation solutions. So let's start with the simplest BRDF in the industry. Earlier, I mentioned lambertian reflectance, but what does that actually mean? From theory, we know that when a light ray collides with a surface, it's going to penetrate it and then get scattered at many angles. For simplicity's sake, we assume that the entry and exit point of the light ray are the same. This is known as a diffuse reflection, when light is scattered all around from the point of intersection. Lambertian reflectance is when the surface diffusely reflects equally in all directions, which is what we're modeling right now as our BRDF, which is still equal to 1. Something else happens when a light ray penetrates a surface though. A certain amount of it is going to be absorbed, never to be seen again, while the diffusely reflected light remains. For instance, if a light ray representing the color white were to collide with an apple, the apple's surface will absorb a large portion of the green and blue light of that ray, while diffusely reflecting the remaining red, giving the apple its red appearance after the reflected light enters our eyes. This is obviously an oversimplification of how light translates to color. For a deeper understanding, refer to my other video on the topic. The RGB color model allows us to represent this mathematically with ease. If the color of the surface is red, then multiplying it against white gives us red, as the green and blue were reduced to 0 0 per the multiplication. Replacing the red with a variable that describes the base color of the surface, we have derived the most basic of BRDFs, the lambertian diffuse. Technically, there should be a divide by pi here, but that's usually omitted in most game engine software. If you care about why, you can read this article linked below. The lambertian diffuse is the most common diffuse BRDF in computer graphics because it's as cheap as you can get. In previous videos, I have shown it with the dot product we discussed earlier, but since it's already present in the rendering equation, we don't need to include it, and we definitely don't want to include it twice. It's named after Johann Lambert, who figured out all of this cosine of the angle stuff back in 1760, but was he actually right? Does the lambertian diffuse BRDF satisfy the rules of the rendering equation? Since the diffuse color and light color are constant, the only actual variable is the angle of incidence, and we know that cosine cannot output a number greater than 1, so it is not possible for this equation to ever produce more than what was put in, which satisfies the law of conservation of energy. The second rule, requiring the BRDF to have the same result if the output and input directions are swapped, is also satisfied by the lambertian diffuse, as it does not rely on the output and input directions at all, so it doesn't matter if they're swapped. The output is the same. Congratulations, lambertian diffuse, you passed the test. You are a solution to the rendering equation, albeit a simple one. With a color texture and normal map, we can already model some ideal diffuse reflectors, such as plaster or unfinished wood, which is why the game I made last video looked decent even though all I was using was this simple BRDF and nothing else. If we try to model something shiny though, like smooth plastic or polished wood, we clearly can't, so we need to add more functionality to our BRDF. Diffuse reflections are just half of the equation. When a light ray hits a surface, not all of it will be absorbed and scattered. A certain amount of it will be directly reflected, which we refer to as a specular reflection. To make modeling easier, we usually separate diffuse and specular BRDFs, so our lambertian diffuse is going to stick around while we develop our specular model. Specular highlights are a bit different from diffuse. While diffuse reflectance scatters at many angles, specular reflectance scatters in a much smaller range, so the direction we view the object from actually matters when it comes to seeing these, as well as the light direction. We should only really see specular highlights when the direction of the reflection aligns closely with the view direction, as that's when the reflected light would be mostly bouncing into our eyes rather than somewhere else. So, if we calculate the reflection vector, we could take the dot product with the view direction, which tells us how close together they are, and the result of that is how strong our specular reflection should be. Not all specular highlights are created equal though. Very shiny objects have tiny pinpoint highlights, requiring a more perfect reflection alignment to be visible, while other more rough objects have a wider range of specular scattering angles, so we can model this by adding an exponent variable that controls how wide the specular lobe is. This specular BRDF is known as the Phong reflection model and was one of the first models for specular highlights ever invented. Back in the day though, computers were much slower, and calculating something like the reflection vector was actually a bit costly. If we take a look at our vector diagram, the normal vector is also the halfway vector between the light and reflection vectors, so we can optimize the Phong reflection model by calculating the halfway vector between the view and light vectors and taking the dot product between the half vector and the normal vector, removing the need to compute the reflection. This optimization was derived by Jim Blinn in 1977, and the resulting BRDF is known as the blinn-phong specular model. Combining blinn-phong with the lambertian diffuse by adding them together gives us what used to be the most common lighting model in video games and other real-time rendering pursuits, because it's extremely cheap and enables us to model a very wide variety of materials in a way that feels physically plausible. Our smooth plastic has the expected specular highlights now, the polished wood actually looks polished, and we could model numerous other materials from shiny to matte, no longer limited to just diffuse reflectors. But is it a solution to the rendering equation? Does it follow the rules? For simplicity, let's take a look at a white surface lit by a white light, since that makes our diffuse BRDF an incoming light equal to 1. The light direction is 45 degrees to the right of the normal vector, and the view direction is 45 degrees to the left of the normal vector, so we'll have a perfect specular reflection. The cosine of the incident angle is about 0.71, and the shininess doesn't matter because 1 to any power is 1. This reduces pretty simply, and we see that the outputted light is 1.42, which is greater than the incoming light received of 1. Aww. Unfortunately, the powerhouse blinn-phong lighting model of the past is not a proper solution to the rendering equation. It breaks the laws of physics and generates more energy than was received. It's also not bidirectional, so it's not correct to refer to it as a BRDF, but who cares? Just because it breaks the rules though, doesn't mean it isn't useful. If you're targeting platforms like mobile where performance matters more than anything, this lighting model is probably good enough for you. Clearly, our simple assumptions of how specular reflections work isn't enough though, and we're going to need to turn to some more advanced theory from physics and optics to get a more physically correct output. This finally brings us to modern day physically based rendering, and what everyone else is doing to make their shading models more physically accurate. Physically based rendering is rendering based on physics. The unfortunate reality is that light operates and reflects at a microscopic level, so if we want to be physically accurate with our light predictions, we're going to have to think at that scale. Physics has found it easier to think about the roughness of a surface rather than the shininess metric that we've been using so far. A perfectly smooth surface like a mirror is going to look like a flat plane at the microscopic level, but a very rough surface like concrete is going to be composed of microscopic grooves of varying slope and height. The greater the variety, the rougher the surface. These little microscopic surfaces are called microfacets, and they average out to the surface normal we've been using for our model thus far. It's these microfacets that light actually reflects off of, not the average of the microfacets, as that wouldn't make sense. We have a bit of a problem though. Computers can't exactly simulate a near infinite amount of microscopic surfaces to do lighting calculations with, so how can we model something that can't actually be modeled? With statistics, of course. If we assume these microfacets are perfect mirrors, and we know from the blinn-phong lighting model that the direction of perfect reflectance is the halfway vector between the outgoing vector and light vector, then we can model the roughness of our surface as the probability that the light hits a microfacet that points in the direction of perfect reflectance. In other words, what is the distribution of microfacets with a micronormal equal to that of the halfway vector between the light and view vectors? This could be any distribution function we want, so we'll declare it as a generic one for now. The next term of the microfacet model is the Fresnel equations, which describe a phenomenon in which surfaces demonstrate greater reflectivity when viewed at grazing angles. For instance, the hallway floor becomes more mirror-like towards the distance as the angle of incidence decreases, and another popular example is the ocean specular. Abstractly, the Fresnel term describes how much light is reflected based off the view angle, which can be any function we want, so we'll declare it as a generic one for now. Lastly, the microfacet model includes a geometric attenuation term, which accounts for the scenario in which microfacets can block each other, reducing the chance of a reflection and causing a phenomenon known as off-specular peak, where the peak reflectance is achieved at a lower angle than otherwise predicted by the Fresnel term. Essentially, the geometric attenuation term counteracts the Fresnel for very rough surfaces. This can be any function we want, so we'll declare it as a generic one for now. These three abstract terms are multiplied with each other and divided by this denominator. Why is this the denominator? Because it's what the most recent literature agrees on. This completes the microfacet BRDF for specular highlights. When we say something is physically based, that means it's derived from microfacet theory. Physically based rendering doesn't always mean photorealistic rendering though, because remember that these functions can be anything we want. They don't necessarily have to follow the real world, it just has to follow the model. As it turns out, Disney derived their BRDF from microfacet theory, so let's finally take a look at how Disney solved the rendering equation. Okay, I lied earlier when I said Disney uses this to model every surface in their movies. They use it for every surface except hair, because hair is just too complicated and deserves its own model. Still, there's enough versatility and value here that Brent Burley presented his team's process for developing their new BRDF model in his SIGGRAPH 2012 talk, Physically Based Shading at Disney. For transparency, this is not the most recent version of their shading model. The one we're about to discuss was extended for Moana and beyond, and the talk going over that was in 2015 by Brent Burley again, discussing the extension of the BRDF into a BSDF to support subsurface scattering. That is beyond the scope of this video though, so we'll put our focus on the foundation for today. Burley's presentation discusses the initial research and design philosophy behind Disney's BRDF, such as the guidelines for each parameter of the shader, and most notably how they fiercely debated the addition of each parameter in the pursuit of having as few settings as possible, which is funny to me because I have the opposite design philosophy. The end model has 11 parameters that control the appearance of the surface, but listing them all out would be kind of pointless, so let's start from the top and build the model piece by piece. The first parameter is the color of the surface. If you remember from earlier, this is part of the diffuse lobe, but does Disney also use the Lambertian BRDF? No, they use a different model for diffuse reflections invented by Burley, known as the Burley diffuse or the Disney diffuse. The Disney diffuse is an extension of the Lambertian model that takes into account Fresnel reflectance, which is dependent on the second parameter of the Disney BRDF, surface roughness. Fresnel reflectance in physics is described by the Fresnel equations, which are extremely complicated, so complicated that Natty Hoffman wrote a paper called Fresnel Equations Considered Harmful. The paper concludes that it's a waste of time to use these Fresnel equations in most rendering contexts, and the only benefit would be seen in spectral rendering, which we aren't doing. So instead, we will go with a simpler approximation. The Fresnel approximation everyone uses was invented by Christoph Schlick in 1994, which models how materials exhibit perfect reflectance when viewed at or under 90 degrees. Essentially, the Schlick Fresnel interpolates from the base reflectance a surface exhibits to the maximum reflectance a surface exhibits based on the incident angle. The Disney diffuse calculates the reflectance at 90 degrees from the roughness parameter, and the angle between the light and half vector, sets the base diffuse reflectance to max, and then calculates the Fresnel based on the angles of incidence from the light and view directions. This is then multiplied with the base surface color, since it's diffused light, and divided by pi. I chose to include the pi this time because I think it looks better. When compared with the Lambertian BRDF, the difference is quite clear. A roughness of 1 makes the sphere look brighter on grazing angles, while a roughness of 0 has the opposite effect because a smoother surface will diffuse less light. Is the Disney diffuse a solution to the rendering equation? Does it follow the rules? No, it fails to conserve energy, which means that the entire Disney BRDF will not follow the rules. But who cares? Remember that the goal is creative control with physical plausibility, not photorealism. The next parameter of the Disney BRDF is subsurface scattering. But Acerola, you said this version doesn't have subsurface scattering. It doesn't. The Disney BRDF provides a secondary diffuse lobe for artists that is an approximation of the Hanner-Hahn-Kruger subsurface BRDF, which effectively flattens the diffuse reflectance and makes it look more uniform across the surface, but it is not a replacement for genuine subsurface scattering, as you can see that the diffuse does not blend into and illuminate shaded areas like genuine subsurface scattering would. The subsurface parameter blends between the Disney diffuse and the subsurface scattering approximation, allowing for more artistic control. The next parameter is the sheen strength, which is an additive lobe based on the angle between the light and half vector, such that when the light is at very grazing angles, there is a slight sheen to the surface, observed on materials like cloth. There is no physical basis for this, it's just an additional artistic parameter, which is accompanied by another parameter that tints the sheen towards the color of the surface. This completes the diffuse portion of Disney's principled BRDF. You can already see how there's way more creative control here than there was with the basic Lambertian diffuse, even if it's not exactly physically accurate. Now it's time to look at the specular portion, which is the cooler part. While the diffuse lobe did not make use of the microfacet model and instead extended the Lambertian diffuse, the specular lobe does derive from microfacet theory. Remember that this means we have 3 individual components that need to be solved: the microfacet distribution function, the Fresnel response, and the geometric attenuation factor. Let's start with the distribution function. There are lots and lots of existing distribution functions to choose from. The 2 most popular are Beckman and GGX, with GGX being most commonly used today due to people saying it looks more physically accurate than Beckman. If you recall from earlier, the distribution function describes the fraction of microfacets that are oriented in the direction of perfect reflection, and this is dependent on the roughness of the surface as well as the angle between the half vector and surface normal. This graph of the distributions shows how much light can be reflected based on how different the half vector is from the surface normal. Remember that the half vector is the direction of perfect reflection, and the surface normal is the average orientation of the microfacets. So this function models how light is more likely to be reflected when the average direction aligns with the ideal direction. As you can see, GGX and Beckman distribution have a similar peak, but GGX sharply falls off and then slowly fades, while Beckman behaves in the almost opposite way, with the distribution actually reaching 0, which GGX never does. There is always at least a little light that's reflected. Disney chose to use GGX for their primary specular lobe, and once we visualize it on our sphere, we get a better idea of how it's working, white corresponds to a full reflection, while black corresponds to no reflection. At a low roughness value, it means we have a smoother surface, and so light is going to more perfectly reflect off of it, resulting in tighter but brighter specular highlights, while a high roughness value flattens out the distribution, resulting in a wider scattering range and a dimmed specular due to less light being perfectly reflected into our eyes. This is when the next parameter of the Disney BRDF comes in, as Disney makes use of the anisotropic version of GGX in order to support anisotropic specular highlights. Anisotropic means that the distribution is not square and varies based on the axis, which when applied to specular highlights results in elliptical speculars rather than the circular pattern you're familiar with. Many surfaces in the real world demonstrate an anisotropic specular response, your own hair being an example, as well as stuff like brushed metals, so this parameter allows for more surfaces to be modeled, as well as provide more creative control over the shape of the specular. The distribution term is the most impactful part, as it's mostly responsible for driving the shape of the specular highlights, but we still need the Fresnel and geometric attenuation term to finish the reflections. The next parameter of the Disney BRDF is the specular strength, which describes the base reflectance of the Fresnel approximation we discussed earlier. Since Fresnel only uses the angle between the light and half vector and doesn't care about the actual surface normal, it looks a little weird when we visualize it on the sphere. It's easier when we look at it on a plane. Remember that brighter pixels means a stronger reflection. Lastly, we have the geometric attenuation term, which counteracts the Fresnel by modeling how microfacets can block and shadow each other, preventing rougher surfaces from demonstrating high reflectance at grazing angles. The attenuation consists of two parts: shadowing, when a microfacet blocks incoming light, and masking, when a microfacet blocks reflected light. Thankfully, the two parts are the same function, just with different inputs. Conceptually, the geometric attenuation function describes the geometry of the microfacets themselves, and the main model for that is the Smith model, which treats the microfacets as a randomized distribution of slopes. Unfortunately, it relies on a specific function derived from the distribution function, but thankfully we already have solutions for the common distributions like GGX and its anisotropic counterpart. Visualized on the sphere, we can see where the geometric attenuation will dim the brightness of the speculars to account for shadowing and masking, with a more uniform dimming at higher roughness values. Now, finally, we multiply each of these together, divide by the microfacet model denominator, and we get our beautiful specular highlights. Of course, we have to add the result to the diffuse BRDF to see both of them in action. This already looks pretty good, but we still have 3 shader parameters left of the Disney BRDF, with the next being the metallicness of the surface. We haven't really talked about metals this video, but unfortunately, they have their own unique behavior when it comes to light interaction. As mentioned earlier, many metals exhibit anisotropic speculars, which our model accommodates for already, but some metals are also known as dielectric, which means they tint the specular reflections towards a certain color, just like how diffuse reflectance tints colors. Lastly, polished metals do not diffuse light, only reflect it. In order to accommodate for the other behaviors of metallic materials, we want our metallic parameter to reduce the diffuse contribution to 0, as well as tint the color of our specular towards the base color. Now we can model metallic materials like gold and silver foil. Our last 2 parameters of the Disney BRDF are for a second artistic specular lobe called the clear coat layer. Essentially, we do all of that specular stuff again, but Disney uses the isotropic GGX distribution for simplicity. The clear coat parameter controls the strength of the lobe, and the gloss parameter controls the roughness of the distribution. The diffuse lobe, specular lobe, and clear coat lobe come together to form Disney's principled BRDF. With this, they modeled every single surface, except hair, in movies like Wreck-It Ralph and beyond. It looks kind of bad sitting in this black void though, so let's put it into a new environment to see what it's capable of. Adding a few lights in a skybox helps quite a bit, but remember that the BRDF is only one half of the lighting puzzle, and it must be paired with a sufficient light transport algorithm to solve the indefinite integral of the rendering equation. In the case of Disney, they get to do path tracing for indirect lighting and global illumination. Unfortunately, we do not get to do that because I am focusing on the real-time rendering context. This means we have to sort of fake indirect lighting, which I did by sampling the skybox from the direction of the surface normal, and then using that as the lighting input for the Disney BRDF, which gives us some simple indirect diffuse and specular highlights to make the sphere fit in more with the environment. I created a few different materials and substance to demonstrate how the BRDF can model very different surfaces, such as dry mud, wet mud, wood, flesh, denim, and metal foil. I put together a little material editor where you can play around with all of the shader parameters, material texture sets, and lights, which you can find over on my Patreon. As usual, a huge thank you to all my patrons. Without your support, I wouldn't be able to spend 10 days straight editing this video. In the end, even though Disney's lighting model breaks the rules and fails to solve the rendering equation, it's still physically based because it's derived from microfacet theory. I hope this has communicated how math comes together like little Legos to produce grander, more sophisticated models that can encapsulate many things at once. Since it's not real, we can make any amount of creative adjustments for more artistic control, or we can abide by the rules to get a more photorealistic result. But at the end of the day, high-fidelity games like Horizon Forbidden West and God of War Ragnarok, which also make use of microfacet theory, are just a few creative decisions and lever pulls away from looking like Disney movies, and that there isn't as much of a difference between them as you'd think. I often hear the sentiment that people don't care for the high-fidelity photorealistic graphics anymore, but just remember that it's through that high fidelity that we get more interesting stylized graphics. All it takes is for someone like you to invent it. Anyways, that's all from me. I hope you have a great rest of your day, and I'll see you next time.